Hello everyone, welcome back to another lessons learned video. Today we're going to talk about the basics of electricity and electric charges. So this first question asks, two charges Q1 and Q2 are separated by a certain distance r. If the magnitudes of the charges are doubled and their separation is also doubled, then what happens to the electrical force between the two charges? So we have a charge which is Q1, so we can represent it with a dot here. So this is Q1. Then we also have another charge, Q2. And they're going to be separated by a certain distance, r. Now, because these charges are here, let's assume that one is positive and one is negative. They're going to exert a force on each other, so each one is going to have a force that is attractive toward each other. So, like that, they're going to be attracted to each other because they're opposite charges. We can draw this about the same size. So, the force that each one exerts on the other can be calculated using this equation. So the distance between them is r, and r is going to be in the denominator, is going to be squared. On the top we're going to start with k, and k is Coulomb's constant, so k is 8.99 times 10 to the 9th newtons meters squared over coulombs squared, and coulombs is a unit for charge. We then have the charge of the first charge, right? The magnitude of the first charge and the magnitude of the second charge. And we're going to take the absolute value of those two multiplied. So if it's positive or negative, it doesn't make a difference. Right? So even if this one were negative and the forces were facing opposite direction, the magnitude of the force will still be the same even though the direction is different. And the units for these, so the charges have to be in coulombs, the distance has to be in meters. In this case it'd become meters squared, but just make sure it's in meters. And then this has these units, the k, Coulomb's constant. Now, the question asks, what happens to the electrical force between these two charges if the separation is doubled and also the magnitude of the charges is doubled? So if we double the magnitude of each charge in this equation, what would happen is that we would have, instead of Q1, we'd have 2 Q1, and then instead of Q2, we'd have 2 Q2. And then if the magnitude is doubled, we'd have 2R2, 2R squared, right? So this R would be doubled. So if we just do the numbers here, this would be equal to K, and then if you multiply the two twos on there, it'll be 4 Q1 Q2, and then on the bottom this would be 4R squared if you distribute the 2 on the exponents. So then the 4's cancel out, and so then you're left with this, which is exactly the same thing as what we started with. So therefore the electrical force remains the same. It does not change. Okay. 3 point charges are placed on the x-axis, and a charge of positive 2 microcoulombs is placed at the origin. A charge of negative 2 microcoulombs is to the right at position as x 50 centimeters, and positive 4 microcoulombs at the 100 centimeter mark. So now it's asking, what is the magnitude and direction of the electrostatic force which acts on the charge at the origin? So we're going to draw our x-axis here, and we have the origin, which is 0 meters, So a 2 microcoulomb charge is at the origin. So we have a 2, and it's positive, right? So positive 2 microcoulombs here at the origin. Then we have a negative 2 microcoulomb to the right. And this is 50 centimeters to the right, and 50 centimeters is a half a meter. And this is negative. And we have a positive 4 microcoulombs at the 100 centimeter mark. So the question now is, what is the magnitude and direction of the electrostatic force on the charge at the origin? So the charge at the origin is experiencing two forces. It's experiencing a force from this charge and this charge. This charge is the same as it, or the opposite charge, right? Because this one is positive, this one is negative. So it's going to be attracted to that first one. So this one is going to exert a force toward it that's going to accelerate it to the right. And this charge 1 meter away is going to be exerting a force that's going to accelerate it toward the left, because they're same charges, so they repel each other. So now to calculate the magnitude of these charges, we can calculate we can calculate this first one. So again, our generic equation is force is the Coulomb's constant, magnitude of charge 1, magnitude of charge 2 over distance squared. Alright, so K again is 8.99 times 10 to the negative 10 to the ninth. Not, or is it negative 9? No, it's positive 9. Alright. Now the first charge is going to be, let's say this one, right? 2 microcoulombs. So 2 microcoulombs, but we said that these charges have to be in coulombs. So to convert it to microcoulombs, we need to do a conversion. All right. So basically 1 microcoulomb is 10 to the 6th. That's wrong. 10 to the 6th microcoulombs equals 1 coulomb. Okay. So you just need to cancel these out. So what you have to do is do 2 divided by 10 to the 6 microcoulombs, which basically gives you 2 times 10 to the negative 6 coulombs. So this is 2 times 10 to the negative 6 coulombs for the charge, this one. Then for the other charge, it's just the same thing, right? It's 2, same magnitude. And the distance between them is half a meter, right? Half a meter. So 0.5, and that has to be squared. So if we calculate that, we get this is equal to 0.144 newtons. This is directed toward the right. If we calculate the force that's going to be accelerating this charge to the left, we still have the Coulomb's constant, and the charge that's being affected has the same magnitude, so that's 2 times 10 to the negative 6 coulombs. The charge that's pushing it to the left, that one is going to be 4 microcoulombs, so 4 times 10 to the negative 6. All right. And then we have the distance here is 1 meter. Right? They're 1 meter apart. So if we do the calculation there, we get 0.072 newtons. Now, because these forces are in opposite directions, we can say that going to the right is positive. We can just define it that way, and going to the left is negative. So then if we add them up, we get 0.144 newtons to the right minus 0.072 newtons to the left, and that should give us a net answer of 0.072 newtons, and it's positive, so meaning it's to the right. So A would be the answer. Next problem asks, 4 equal charges are located at the corners of a square of side D. If the magnitude of each charge is doubled, what happens to the resultant force on each charge? So we have a square here, right? And we have 4 equal charges, so let's just assume that they're positive. We can also say they're negative, but it'd have the same effect, right? So you have these charges, and they're the exact same magnitude and sign, because they say that they are equal charges. If the magnitude of each charge is doubled, what is the resultant force on each charge? We can just take the resultant force on one of these charges, right? The resultant for each charge is going to be dependent on, again, the equation we talked about. Now this one is going to experience a lot of charges, right? You're going to get a force from this one, a force from this one, and a force from this one. And the side length is D here. But this one is not D, right? This one is actually different. This one would be, if you use Pythagorean theorem, right? D squared plus D squared, and then you square root it, and it should become that. That should be D2 squared, or 2D squared. And so that would give us something like that, right? You can solve this problem out the entire way, and I will here. But basically, all you need to really understand is that in all the 3 equations that are going to be basically defining the force on this charge here, you're always going to have Q1 and Q2. So if you double the magnitude of the charges, that would give you 2Q1, 2Q2, and then this would just be 4K Q1 Q2 R squared. So the 4 is the only thing that's changed from before. So it would just be quadrupled. But if you want me to prove you that, I can. So we know that there's a force pushing it to the right, and that's going to be Coulomb's constant. We can double these, right? And the distance would be D. And so this would be this first one. For the second one, we can define this one as second, right? It would be the exact same thing. And it should be like that. And for the third charge, which is this one, and these are going to have directions. So this one would be 0 degrees, this one would be 90 degrees, and this one would be 45 degrees. Right. So notice how in all of them, if you just have a 4. So there's you get a 4, there you get a 4, there you get a 4. So it's going to be quadrupled at the end. The force of attraction between a negative 40 microcoulomb and a positive 108 microcoulomb charge is 4 newtons. What is the separation between these two charges? So here we need to find the R. Right. So we know the force is 4 newtons, and Coulomb's constant is 8.99 times 10 to the 9th. And the first charge, at least one of them, is 40 microcoulombs, and that's going to be 40 times 10 to the negative 6 coulombs. And then we have one charge that's 108 microcoulombs. Yeah. So now we need to find R. So if you just take R and put it here, and then do that, and then square root this whole thing, you will then get rid of the squared there. You will get 311 596 meters, and so that's about 3.12 meters. Alright, so this question doesn't fit on the page, so I have to extend this out. Figure 1 shows 3-point charges of magnitude 2 microcoulombs, 3 microcoulombs, and 4 microcoulombs are located at the corners of a triangle. The resultant force on the 4 microcoulomb charge is given by which one? So this is one that involves vectors. So we need to really take into account the force created by each charge on the 4 microcoulomb charge. So this is the 4 microcoulomb charge on top. We're trying to find the force by both of them. So there's going to be a force this direction by this this charge, and there's going to be another force in this direction. And they're all positively charged, so that's why they're pushing out on it, because they repel it. To find the magnitude and the direction of each force, we can go ahead and set it up like this. So this is the force on the left, and this is the force on the right. Now the force on the left is going to follow, again, the same equation. So the charge being affected is 4 microcoulombs, so that's 4 times 10 to the negative 6 coulombs. And it's being affected by a 2 microcoulomb charge, so that's 2 times 10 to the negative 6 coulombs. And the separation there is 20 centimeters, however, this would become 0.2 meters once you convert it to meters. Now we need to figure out a direction for this charge. What is the direction for this charge? If you imagine a x and y axis, and I should draw it in different colors so you can see the contrast a little bit. Right. If you, and our calculators work like this, right? If you take this point, this direction, to be 0, and like move upwards, at this point you had 60. So this is 60 degrees. So and the force is in the same direction, right? Here, this force. So the force is 60 degrees. That's the angle of the force. Now for the second situation, we also have Coulomb's constant. The charge being affected is the same one, but here the magnitude of the charge that is creating the force is 3 My pen is stuck. Hold on. 3 times 10 to the negative 6. And the distance there is the same. 0.2 squared. Alright. Now we need to find the angle of it. So how do we do that? If you imagine again a y-axis and then an x-axis. If we start out at 0 here, and then we move here and we get to 90, right? And we move here. I'm going to zoom in here so you can see. We have 60 degrees here. This is 60 degrees. Meaning if this whole thing, and this is 180, so this whole area is 90 degrees. And if we've gone 60 here, that means there's 30 here, right? And so we've gone 90 and we go an extra 30, that's 120. So there's 120 degrees angle with this, and you always want to have the right side positive x-axis as your starting point with these. That would make it easier once you need to plug things into your calculator. So this is a problem. Okay. So now let's go ahead and set up the components of the vector. So the way we do that is, if I can just extract, there we go. I missed the negative sign there. Let's not do that. Okay, that's a problem. Forget the negative sign. I will re-add them. So this will have components like this. It'll have an x component and a y component. And the way you figure that out is by doing the magnitude that you get here and multiply it for the x component. You get the magnitude and you do it by cosine of the angle. So in this case 60. And then here it'll be the same thing but the sine of the angle for the y component. So let's first find the components. So if you put this into your calculator, which I will do now, you'll get the magnitude of the chart of the force. So that gives us 1.8 newtons. And if we multiply 1.8 newtons by cosine of 60, we will get 0.9 newtons. And if we multiply 1.8 newtons by sine of 60, we will get 1.56 newtons. So those are the components for this first one. For the other force here, we're going to get some different components. So we're going to get the same thing again, but in this case we can draw it, I guess. Kind of running out of space. Yeah, this is not good. Right, so we're going to have on the y component cosine of 120, and then cosine, or really sine of 120 for the y component. The x component is cosine. So here again we would find what this is. This would give us 2.7 newtons. So now if we multiply 2.7 newtons by cosine of 120, we actually get negative 1.35 newtons. And if we multiply 2.7 newtons by sine of 120, we get 2.34 newtons. So now if we take these components and we add them up, so let's copy them down. All right, 1.35 negative 2.34, 0.9, 1.56. If we take them and add them, we get 3.9 newtons for the y component, and then we get negative 0.45 for the x component. So now we have to figure out what it is without the components. So in order to do that, we can basically take the y component over the x component and then put that inside of a inverse tangent function, and that should give us the magnitude of it. So if you do that on your calculator, 3.9, and this should have a newtons if I put it on top as well. That actually gives us the angle we need. So this gives on the calculator negative 83. So if you imagine an xy axis again, this gives us negative 83, which is around over here. But what you should also think about is that with inverse tangent, when it gives negative 83, it could also be 180 degrees added to that, so it could be over here as well. And this new angle here, this is 97 degrees, right? Because you've gone 7 degrees missing here, and similarly 7 degrees missing here. Now we just need to find the magnitude. That was finding the angle. So the magnitude would be simply Pythagorean's theorem, I believe. 3.9 squared plus 0.45 squared should give something like 15.4, and then you square root 15.4 and we get 3.9 newtons. So we know it can't be one of these. So it must be either A or D. And they're asking, they give the same numbers, but one is with respect to the positive x-axis and one is the positive y-axis. As you can see, our system of doing the angles is from the x-axis, from the positive x-axis. So it wouldn't be the y-axis, it would be the x-axis. So A is the answer there.